what if there's only one charge present? If there's only one charge, there's no force, because Q2 would be 0. But we'd still like to be able to describe that physical situation as though we're thinking about what would happen if you hypothetically put a charge in the vicinity of a charge that already exists. So we're going to say that we have one charge here. And that brings us to the idea of a test charge. I'm going to use little q for a test charge. In your book they use q test, but that's a lot of extra writing. So little q is my test charge. The idea of a test charge is that it is so small that it doesn't cause anything else in the problem to move. And if we do that, then we can describe the electric field around this charge Q by saying, what happens if we just talk about the force that would be experienced by this test charge proportional to the value of the test charge. So the electric field at some point P is going to be the force on the test charge divided by the value of the test charge. And what you get then is big Q divided by 4 pi epsilon naught r squared a hat r, where this vector r then is the vector from Q to your observation point P. And you can move your observation point around that way and test what the value is of your electric field by figuring out what force would be exerted on your test charge at that location P. The units of this electric field are newtons per coulomb, which simplifies to volts per meter. That's kind of wild, but you'll see more about why that's true in a later chapter. Usually we actually end up using volts per meter. Nobody ever refers to an electric field as newtons per coulomb, but that's what the two things simplify to. Some definitions of the electric field actually use a limit, and they do that to emphasize that adding the test charge should not perturb the problem. It shouldn't move anything around or change the value of the forces on other objects or anything like that. And the way you write that down looks like this. It's the limit as the value of Q goes to 0 of that force on Q divided by the value of Q. The result is the same. You still get Q over 4 pi epsilon naught r squared a hat r. Now there's a key thing to note here, and that is that this is the electric field due to a point charge. Other problem configurations have different electric fields. And we're going to talk later about how we figure out what those electric field values are. But if this was the electric field all the time as the solution to every problem, there would be no reason to have this class. This is sort of your building block for the electric fields in a lot of different problems, because the electric field due to a point charge is what we make all other electric field solutions out of. And that's superposition in a nutshell. So let's generalize this expression a little bit more. For if you have a point charge at some position, so let's say I draw a coordinate system here. That's my x-axis, that's my y-axis, that's my z-axis, and I have a point charge right there at a position that I'm going to name r prime. And I would like to know what the electric field is at some other location. I'm going to change colors there. At some other location, R, then the distance between the vector from R to R prime, the vector from the charge to the observation point, then the vector from the charge to the observation point, which is R, is equal to the difference between those two vectors. So it's going to be little r minus little r. Whoops, that's not a little r. Little r prime is what gets you that vector from the one location to the other location. And as a result, the electric field, as a function of position r of the observation point, is the value of my charge, which is at location r prime, divided by 4 pi epsilon naught r squared a hat r, which you can write in terms of their individual positions relative to the origin as q over 4 pi epsilon naught magnitude r minus r prime squared times the unit vector, which we're also going to write as r minus r prime divided by magnitude r minus r prime. So this magnitude is the value of r squared, and this term right here is our unit vector expressed in terms of the individual positions of the charge and the observation point. What happens if you have multiple charges? You can just add up the electric field contributions from each of the individual charges. The total electric field is equal to the sum over all the charges that exist. Let's say there's n charges of the electric field due to each of the individual charges by itself. So that works out to sum from I equals 1 to n q sub I, because they might have different values of charge, they might have different amounts, times r minus r sub I. The observation point here does not change, but the location of each individual point charge can change, divided by 4 pi epsilon naught. Those values don't change. Magnitude of r minus r sub I cubed. It's cubed here because in the previous expression I have it squared right there and then another factor of it. So when you combine those, you get the little cubed. this sum itself is a statement of the property of superposition. The fact that the field due to a bunch of point charges is equal to the sum of their individual electric fields, that's superposition. That is valid in linear media, which is true most of the time. We'll talk more about that later.